Welcome to AI Podcast. I'm Ben, and today we're diving into a fresh AAAI paper called LLM+AL, Bridging Large Language Models and Action Languages.
And I'm Ava. Right off the top, what's the one-line takeaway for listeners rushing between meetings?
The punchline is this: let the language model write down what the world looks like in a formal action language, then hand the heavy lifting to a logic solver, and keep a feedback loop that helps the model fix its own mistakes. That combo makes solving planning-style problems more reliable than using a language model by itself.
So the model is like the author of the rules, and the solver is the referee that enforces the rules.
Exactly. The paper is by Ishay and Joohyung Lee, based at Arizona State University, with Lee also connected to Samsung Research.
Nice. Before we get too deep, what is an action language in plain English?
Think of an action language as a compact way to describe change. You list what things exist, what can change about them, and what actions cause those changes. The specific one here is called BC+. It's declarative, which means you don't write step-by-step procedures. You declare truths and constraints, and a solver figures out which sequences of actions are actually possible.
And that helps because language models are great at describing things, but not so great at checking all the knock-on effects, right?
Right. When you rely on a language model alone, it might spit out a plan that looks plausible, but breaks a hidden rule along the way. An action language plus a solver won't let that slip through, if the rules say you can't have two objects in the same place at once. The solver will block any plan that violates that, no matter how confidently the model proposes it.
Got it. The paper's title says Bridging Language Models and Action Languages. What's the bridge exactly?
The bridge is a pipeline they call LLM+AL. First, the model reads a natural language puzzle and proposes a signature, which is just the catalog of objects, properties, and actions. Second, it writes down the rules in BC+. Third, it formulates a query, like find a plan that gets everyone across the river. Then comes the key part, a self-revision loop. They run the rules through a solver. If the program fails or the query doesn't check out, the solver's feedback is fed back to the model, and the model revises the rules or the query.
Like test-driven modeling. You write a spec, run the tests, get errors, fix the spec, repeat.
Exactly. And because the rules are declarative, the errors are easier to diagnose than in a chunk of ad hoc code. You might fix one causal law or add a missing state constraint instead of rewriting a whole search algorithm.
What kinds of problems did they try?
Classic reasoning about actions. Missionaries and cannibals and elaborations of it. River crossing puzzles. Tower of Hanoi variants. And even some Sudoku cases, including ones where no solution exists. The point is not just to find a plan, but to respect constraints and to recognize when a plan cannot exist within a reasonable bound.
That last bit matters. People often ask, can the system tell me that there is no plan, or does it just keep searching forever?
Exactly. Here the solver can certify something like, there's no plan up to a certain length. It's not a proof of impossibility in an infinite sense, but it's a practical and useful certificate.
How did this stack up against strong language models used on their own?
In short, better. When you ask a model to just reason directly in natural language or to write some quick procedural code, it tends to miss corner cases or invent steps that break constraints. With LLM+AL, more tasks were solved correctly, and false confidence dropped. The self-revision loop also slashed the number of basic program errors, like syntax mishaps or missing rules.
That sounds promising, but let's sanity check. Did this require human help?
Sometimes, yes. The system often got close on its own, and in cases where it fell short, a small number of human edits to the rules cleared things up. Think of it like nudging the model to add one missing precondition or to tighten a constraint.
So it's not push-button magic, but it's more steerable and fixable.
Exactly. The author's message is that a declarative model is a friendlier surface for human-in-the-loop debugging than opaque chain of thought or brittle code generation.
Let's unpack why this approach helps. Conceptually, why is declarative modeling such a big deal here?
Because it separates what the world is from how you search it. In a declarative setup, you say, here are the facts, here are the constraints, here's how actions change things. The solver handles the how. With imperative code or free-form reasoning, the model is responsible for both the facts and the search strategy, which is a lot to juggle and easy to get wrong.
Give me an analogy.
Imagine planning a trip. Declarative is like handing a travel agent your constraints. I must arrive by noon, I can't take red-eye flights, and I need one checked bag. The agent searches options and returns the valid itineraries. Pure language model planning is like having a well-spoken friend try to invent a route from memory. Charming, but they might accidentally book you on a flight that lands after your meeting.
Been there. What about the action language itself? Why BC+ and not something like classical planning languages?
BC+ is comfortable with defaults, ramifications, and state constraints. For example, if you move a boat, by default it's no longer on the original bank, and if two people are on the boat, they end up where the boat lands. Those are the kinds of indirect effects that pop up all the time. Some traditional planning setups can model them, but it's often awkward. BC+ is designed to say those things cleanly, and the solver enforces them consistently.
And the self-revision loop is really the glue.
Right. The loop gives the model grounded feedback. Instead of vibes-based answers like try again, it gets concrete signals like this rule makes the program inconsistent or this action is missing a precondition. That makes the next revision targeted.
I'm curious about the limitations. Where does this approach not go yet?
Scope, first of all. The experiments are on carefully designed puzzles, not open-world robotics or messy web environments. Second, the guarantees about unsolvability are bounded. The system can say there's no plan up to n steps, but proving there's never a plan is a different beast. Third, the pipeline uses a particular large model under the hood, so portability to other models and full reproducibility need careful attention. And there's still some human effort when the model's first pass is incomplete.
If you had to suggest next steps for the community, what would you push on?
3 things. 1. Take this into interactive settings like simple robots or web agents, where the world pushes back and you have partial observability. 2. Extend the modeling to uncertainty and non-deterministic actions, because real environments aren't deterministic puzzles. And 3. Better tooling. Imagine an IDE where the model proposes edits, the solver explains failures in plain language, and a human approves changes with one click.
I like that. It turns the LLM into a knowledge engineer that drafts the theory of the world, and the solver as a consistent, somewhat grumpy, but very helpful colleague who says, sorry, those rules don't add up.
Grumpy but fair. Also, the paper's error analysis is useful. By classifying where things went wrong, like missing signatures or misspecified rules, they show where training or prompting could be improved. That sets up targeted research rather than hand-waving.
Let's bring this back to a concrete example. Missionaries and cannibals is the classic one. In plain terms, the rules say the boat moves, people board, and disembark, and you never leave more cannibals than missionaries on a bank unless there are 0 missionaries there.
Exactly. In a pure language model solution, it's easy to suggest a sequence that looks fine, but leaves a bank in a bad state for one step. In BC+, that illegal state is banned by a constraint, so the solver never proposes it, and the self-revision loop steers the model toward a set of rules that avoid it entirely.
And if a variant is unsolvable under a step limit, the solver can certify that, which is way better than a shrug.
Right. That's a real user experience win. Knowing there is no plan up to a reasonable horizon is often the decision you need.
All right, quick recap for listeners. LLM+AL pairs a language model with an action language called BC+, and a logic solver. The model drafts the rules, the solver checks them, and a self-revision loop closes the gap. On a suite of planning-style puzzles, that setup was more dependable than an LLM on its own, and could even tell you when no plan exists within a bound.
And the caveats are sensible. It's mostly puzzles for now, the unsolvability claims are bounded, and sometimes a human nudge is needed. But the direction is compelling, especially for anyone building agents that must obey constraints.
Final takeaway. If you let the model do what it's good at, capturing structure and common sense in language, and you let a formal system do what it's good at, enforcing laws and searching systematically, you get a smarter, steadier agent.
Well said. That's it for today's AI podcast. If you enjoyed this breakdown, share it with a colleague who loves both logic and language.
Thanks for listening. See you next time.